Hello everybody, this is the fourth video in a series of videos on Python programming for engineers. My name is Mark Bakker and I work at the Delft University of Technology. Today's topic is functions. As an example, we're going to build a Python function for this mathematical function f of x is equal to h0 times e to the power minus x over alpha, where h0 and alpha are constants. To define a function in Python, we need to use the def command. After def, we need to provide the name of the function. Let's call it test. After that, we need to provide the arguments. First open the parenthesis, we give it the argument, which is x, and we don't have to give it any other arguments right now. We close the parenthesis, and then we need to enter a colon. Then we hit enter, and you see IPython automatically indents. We are now inside the function. Anything we type in here is what will be executed when we call the function. When we are done with the function, we stop indenting and continue from there. Alright, the function. What do we need? We need to define what h0 is. h0 is, for example, 4.0. We need to define what alpha is. Alpha is equal to 10.0. And then we need to calculate this f. F is equal to h0 times the exponential function is called exp of minus x divided by alpha. And now we're kind of done, but we need to tell the function that we want to return this value, this what we call f, the variable f. We want to return that to the user when he calls the function. So we type return, which is a Python command, and then f. We hit enter, and you see IPython right away stops indenting because it realizes, oh, we've done a return, so we must be done with the function. We can now call this function by its name, test, and we need to provide it the function, the value of x, for example, 4. And we want to print that value to the screen. Well, let's first calculate test at x equals 0. Then we want to print test maybe at x equals 4 and print the test at x equals 8. We can call it as many times as we want. If we hit shift enter now, you see at x equals 0 it gives us the value 4, and that's the correct value. If you look at this function, when x equals 0, the e to the power 0 is 1, so f is equal to h0, and we defined h0 here as being 4.0, so that's the correct value. And you see it goes down when x increases, and that's what you expect. This function can actually be called with an array. X is equal to linspace, say from 0 to 40 and 100 steps. And we can calculate h is equal to the test function with all these x values. And once we've done that, we can plot x versus h. Shift enter. There's our function. And that looks about right. It's an exponential decay. At x equals 0, the function value is 4. It nicely goes down. At x equals 40, it's almost 0. And if you look back here, at x equals 40, we get e to the power minus 40 divided by alpha, which is 10. So it's e to the power minus 4. Well, that's almost 0. So it looks like we're doing it correct. Notice that when we call our test function and we open the parentheses, then it gives us help. It tells us test of x, and it also tells us there's no docstring. And that's indeed what we've defined here. Test has only one argument, it's called x. But this is not a very helpful docstring. We could improve the docstring by entering something more useful. And to do that, you have to type triple quotes. They can either be single one or double ones. Triple quotes, and then whatever docstring you want to type. For example, this function computes h0 times e to the power minus alpha times x. And then you end again with triple quotes. Now, if we execute this function, notice now this input argument is now number 3. We've run this function again when we call test now here, when we open the parenthesis. and we wait for a second, it nicely tells us this function computes whatever we type there. So we can add docstrings. There can be multiple lines. There can be a whole paragraph if you wish that explains what the function does. The other thing we have to talk about is these variables inside the function. H0 and alpha are defined inside the function. That means they are not accessible outside the function. If I type here print alpha and I hit shift enter, I get an error message. Name alpha is not defined. Why is that? Well, alpha is defined inside the function. It can only be used inside the function. The outside doesn't know about that variable. It works the other way as well. If you type here alpha is equal to 5 and we call our test function again, for example test at x is equal to 8, we're going to get the same value back of 1.79, which is calculated with an alpha of 10. As you can see here, the same 1.798, because it doesn't use this alpha. This alpha is the alpha outside the function. This is the alpha inside the function. Even though they have the same name, they are totally different variables. One is defined outside the function, the other is defined inside the function. Let's modify this function somewhat more. It would be nice if we could actually specify H0 and alpha. And you can do that by defining it here. More arguments. We can define H0 and we can define alpha. If we do that, we don't need to define it here anymore. What would be even nicer is if we make these keyword arguments. If we provide, and keyword arguments is very easy, if we simply provide here H0 is equal to 4.0 and alpha is equal to 10.0, that means that they are now keyword arguments. And keyword argument means that you can define them, but you don't have to define them. If you don't define them, it uses these default values. So if we run this script again, it will still provide the exact same numbers we had before. Test 0, test 4, and test 8. It's going to give these three values, so run it. And you see, indeed, it still works. Wasn't very exciting because nothing changed. But you can also call this test 0 with H0 is 4.0 and alpha is 10.0. That will run as well. Or we can change the H0. Let's make it 20. I see, now it changed here to 20, right? It was 4. It runs with 4. When you provide a different value, it uses that value. Notice that the test 4 and test 8, I didn't define the keyword arguments there. They run with the default values that are provided here. The nice thing about these arguments are that the keyword arguments are that you can specify them, but you don't have to. You don't have to define them. You don't have to define every single one. We can just define H0. For example, you can define alpha before you can define H0 if you want to. Also works. So the order of the keyword arguments is not important. You can choose the order you like, and you can specify the values you like. The only thing you have to do is you have to make sure that you first define the regular arguments, like x is not a keyword argument, it's just an argument. It doesn't say x is equal to something default, so you have to provide x. If you don't provide x, let's try that. So we just divide that. We get an error message, test takes at least one argument, x, and you give 2, this one and that one, but they are keyword arguments. Might not be the most useful error message you get here, because it says takes at least one argument, 2 given. Well, there are 2 keyword arguments given, but no regular one. So we have to provide a regular one as well. And you cannot put the regular argument after the keyword argument. That's not allowed either. Let's try that. So we provide here the x, first 2 keyword arguments and then the regular argument. Maybe add some spaces so you see where they are. Shift enter. Non-keyword argument after keyword argument. That's not allowed either. Right? So first the regular arguments, then the keyword arguments. The keyword arguments can be in any order you want. You can define whichever one you want. And the ones that you don't specify, we will use the default value. Next, we're going to make a slightly more complicated function by modifying the function we just created. This is the function I want to create. For x larger than 0, we use the function we already created. But when x is smaller or equal to 0, you're going to use this slightly different function that's minus h0 times e to the power plus x over alpha plus 2h0. This function together is actually continuous, and its first derivative is also continuous as x equals 0, so it's going to look like a smooth function. To make this, we're going to have to modify our test function we have here. We now have to say when x is larger than 0, we're going to make f equal to h0 times x of minus x over alpha, else, if x equals larger than 0, else f is equal to, and now we get our new part of our function, that's this part, minus h0 times x of x divided by alpha plus 2 times h0. And after that, everything will work just the same. We can run this. And you see, it still works. We still get an answer. If it works, we don't quite know yet. Let's test this function out at just 0.0001 and also at minus 0.0001. So we can see whether it does give the correct value. And indeed, it's almost 4 here. It's just beyond 0, and it's almost 4 there, so it looks like the right one. Maybe just to show that it indeed works, we can add here 2 print statements. Print hello, x is larger than 0. And here we print hello, x is smaller than 0. And these are statements you would normally kind of put into debug code, but I want to just show you it works. Indeed, we first call it with 0.0001. It says hello, x is larger than 0. It will execute this f and return that f. The second time we call it with a negative number. It will go to the second part, x is now smaller than 0, and return the value of this part of the function. Looks like that worked fine. We can leave. No, we don't want to leave those print statements in because it's going to bug us when we want to call this function with more x values. Let's try to plot the function. I already have the code here. X is a linspace, but now we don't want to go from 0 to 40, but from minus 40 to 40 with 100 steps. H is equal to the test of x. We're going to plot x versus h, and we can remove these statements that were leftovers from before. We hit Shift Enter, and we get an error message. Let's see. When you look at error messages, always start reading at the bottom. And it says, the truth value of an array with more than one element is ambiguous. And what do we have? We say here, if x is larger than 0. I can see why that won't work, right? You pass it here 100 x values. Some are negative, some are positive. It says if x is larger than 0. Well, it doesn't know what to do with that, right? Because part of the array is larger, part of the array is smaller. It can't do that. But we still want to compute this test function at these 100 x values. How do we do that? Well, for that, they invented a nice function called vectorize. We can vectorize the function, which means we can call it with an array of input arguments. And to do that, we create a new function that's called test_vec. It's the vectorized version of test, but you can call it whatever you want. And then the command is vectorize, that's a function, and we give it the function that we want to vectorize. It's called test. Now test_vec is a new function. And that new function calls test with, and if you provide input arguments and it's an array, it will call it many times as the array is long. So now we can actually call test_vec with this array of 100 x values stored in h, plot x versus h, and we get a very nicely smooth curve. You see at x equals 0, it is indeed 4. When x becomes large, it goes to 0, large positive. When it becomes large negative, then this part of the function goes to 0, and we end up with 2 times 8, 0. 8, 0 was specified by default using the keyword argument to be 4. 2 times 4 is 8, and by golly, in a function here, it's 8. That's all I got for you today. I hope to see you next time.